What I have shown here is a position vector r in space and a force vector f in space and the resulting moment. The moment is obtained as a cross product. So r cross f. We'll see this a lot, and these are vectors. In the book, vectors are indicated with bold letters, but for doing your homework, etc., the arrow over the top of the letter is a better indication that this is a vector. And the resulting moment is shown here, and the magnitude of this moment. And we get the magnitude of this moment from a dot product also. So two types of products we'll be interested in with vectors, the cross product and the dot product. And we'll see some of the features of those here. Now that you've had a chance to look at this, I've drawn some vertical dashed lines from the endpoints of the vectors so you can kind of tell where they are in 3D. But again, in 3D, it's sometimes more convenient to rotate the view. And if you rotate the view, you can see the force vector. The light shaded vector is just a force vector moved to the origin, and you can control its position by moving its endpoint or its value. Or you can enter numbers over here on the side. A couple of features, again, about cross and dot products that we'll see are the projection first. If we extend our position vector to a full line, we can see a projection of this force vector in the direction of our position vector. This is fairly useful. To do that, again, we use the dot product. So we have r dot f, and that's calculated by taking each direction component, rx fx plus ry fy plus rz fz, and multiplying them together. We can also do the calculate the force vector in the r direction. We take the r vector divided by its magnitude, and we have this r dot f, and we need to divide that by the magnitude of r. Since the magnitude is the square root of the product of the r's, we can actually replace these two magnitudes by an r dot r. So we can simplify our computation a little bit in this manner, because this quantity inside parentheses is the magnitude of our projected vector f onto r. And another way to compute it is to use just the direction vector lambda r, which is this r vector divided by its magnitude times this product. Now we'll see if we look at this, we also could use the angle here between the r and f vector. So we know that cosine of theta times this f vector gives us the magnitude of our fr vector. So we could have cosine of theta inside this parentheses times the magnitudes of the two vectors. To get the perpendicular vector, we just subtract our vector projected onto r from our original vector to get the perpendicular vector. This perpendicular vector will give us the same moment if we cross it. So if we cross r times this fp, we'll get the same moment that we have to start with, which is an interesting feature. Now, another thing with moments is we have a line of action. So our line of action here, go back to the original view a little bit, is a line drawn through our force vector. So we draw a line through our force vector, and we see the angle between the vectors is shown here. Let's go back to default view. You can't see much of the angle in this view, but now if I move this vector along its line of action, we'll see that our r vector changes as we move, because we're changing the position, but we notice that the moment vector doesn't change. It stays the same as we move all the way along this line. So now let's look at the angle between these vectors. I've redrawn the r vector, moved it out along its line of action a little bit, and we'll look at the angle between these vectors. We see that this angle, again, can be computed from a dot product. So we can have cosine theta times our r dot f divided by the magnitude of the two vectors, which is really just each unit vector dotted together. And we can find this angle in this manner. Here, this angle is 76 degrees, and we see it gets smaller up there to 20 degrees. If I move it down here, it's more. An interesting thing is that cosine theta is 0 at 90 degrees, and r dot f is also 0 so theta is 90 degrees. So that's fairly important. We can actually use that feature, knowing that it's 90 degrees here. If we look at the magnitude of r now drawn from the origin, and we see that as we move our force vector along the line of action, again, the magnitude of r is changing, but the magnitude of r now is minimum when the vectors are at 90 degrees. So the minimum distance is when sine is the biggest. Sine is 1 at 90 degrees. So we can compute this minimum distance between the point and this line of action of F. So we can just draw a force along this line of action and use this computation to calculate our minimum distance.